Shall we start? How are you doing? The last comrades of the army of deep learning, right? Okay, so we talked about the sequence data last time, right? So we talked about the fact that in practice, usually we have sequence data. And sequence data has this property that we are trying to somehow understand labels. So we want to understand the output, but this is coming from a sequence which is generally carrying some sort of temporal correlation. So we used the word temporal correlation a couple of times last time. So if we want to officially define what does temporal correlation mean, it simply means that when I have a sequence, so if I have a bunch of, say, vectors or any object, but I have a sequence of them, so now they depend on time, everybody through time is depending on the others, right? So like every guy at one particular time also carries information about the guys before, right? So now you have a good feeling about XT, right? So you know, for instance, XT could be a part of your voice, or it could be a frame of a movie, right? Or it could be a part of a text or something like that. So now the question here is that how we can assign label to this sequence. So when we have a sequence problem, the problem is not as easy as before. So it's not like you have a input and then the input has always one specific label, right? So the labeling now is going to be different, and this is one of the key challenges. So in practice, we could have different kinds of sequence problem. And this is, even though we call it different kind of sequence problems, it's essentially different kinds of supervised learning problems that you could have. So you could just talk more generally about the whole supervised learning idea. So the first type is the type of many-to-many. I call it type 1. So this is my naming, many-to-many type 1. And what does it mean? This is the favorite one, the easy one that you always think of when you start thinking about sequence data. Meaning that I have a sequence x1, x2 till xt. Everybody goes at a particular time inside the neural network. The neural network has the memory from before, so the hidden state of the previous time. It has it as well, and then it's going to generate you an output, and that output corresponds to that particular time, right? So this is many-to-many problem type 1. This is easy. Speech tagging is a kind of typical application. So you have a speech, and you are just making it into the right frame, so every frame contains one word or one part of the speech, and you want to say what kind of thing is that part, right? Or if you have a text and you are just breaking it down into words, you want to say what is the label or what is the role, case, whatever, of that word inside the sentence, right? I am good. I is subject. Am is verb. Good is adjective. So you can just give label to every single word, right? So here, every single input has one particular label. So this is the easiest kind of many-to-many problem you can think of. But you could have such a problem, right? So you could have multiple inputs through time, a sequence, input sequence. You could have multiple output, again, an output sequence. But they are not totally aligned, right? One particular example is speech recognition, right? So you're listening to an audio, and you want to find out, okay, this part of the audio is talking about science. The next part is talking about history. The next part is talking about sport, and so on, right? So there is no need that every part is exactly the same size. There is no need that every single frame you give into this neural network going to get labeled with one thing, right? You wait till the whole part of the speech is over, then you're going to label it, right? And then you go for the next part and so on. So you start from beginning, and then at some point you're going to get, okay, here is the science part over, and now you go ahead, okay, the next part is over, and so on. For instance, when you watch YouTube, sometimes YouTube does it automatically on the videos, right? It's going to segment it into parts. Like the first chapter is here, the second chapter is from this time on, and so on, right? So this is the other kind of many-to-many problem. Another kind of many-to-many problem is this kind. Like you start to give a sequence to your network is going to observe all of this sequence, and then when you're over, it starts to just generate one sequence as an output label, right? For instance, best example, translation, right? If you want to do translation, you wait the whole phrase or statement in one language come into your neural network. Once it's over, then your translator starts to just translate, right? So your English, or I don't know, your German sentence is over, now the English translation is coming out, right? So this is the third type of many-to-many problems that you can imagine. You do not need necessarily to have many-to-many problem. You could have one-to-many problem, right? So you could have one single input. So your input is a sequence of length 1, but your output is a sequence again, right? And you don't call this problem, again, a feed-forward problem, a one-to-one problem that we had before, because your output is going to be a sequence, and sequence means that you carry temporal correlation, right? So Y2 is basically needs to know what was Y1, or somehow get some information about Y1 to be generated, right? So it's not simply that I would say this whole thing is one label to one input. This is not the case, right? Good example, image captioning, right? You put an image, my image alone sitting in my office, and then it should be a sentence, right? This poor guy is sitting in his office alone, right? So this poor guy, poor should knows this, right? Guy should knows poor, and so on. This is not one label, right? It's a sequence at the output. So your input could be simply one image, but your output could be a long sequence. So this is what we call it one-to-many problem, and you could have also a many-to-one problem. For instance, you ask ChatGPT to just give me one image. I mean, ChatGPT does it using DALL-E, but anyways, you can ask a neural network or a machine to just give a description, or I don't know what is the example. Sequence classification I put here as an example, but you can also give description of something to your machine, and then the machine going to generate the image for you, right? Generate an image of a poor guy sitting alone in his office, and then it's going to be me in the middle of the office, right? So you could have many-to-one problem as well. So this is different types of the problems that we could have with neural networks when we think of sequence data, and essentially what we had up to this point was one-to-one problem. So we were actually working in a fraction of the whole possible cases that we could think of up to this point. Because essentially we can think of every single data point that we had up to now to be one sequence of length 1, and then the corresponding label is also one sequence of length 1, right? You could also say that, okay, I put whole of my data set as a complete sequence, right? But this sequence does not carry any temporal correlation anymore, right? So x1 is independent of x2, x3, and so on, all of MNIST images. And then the outputs are independent as well, right? So essentially, you don't need any memory. You can just get rid of those connections over time. And this is essentially what we did up to now, right? You didn't think of it like a sequence. You thought of it in this form, right? So every MNIST image is one input, and the corresponding label is the output, right? But you could put all of those, I don't know, 60K images inside MNIST. You put it as a long sequence, and you have a long sequence at the output. If you just try to minimize the empirical risk, you're going to end up with the same formula, right? So up to now, we were working with one-to-one problem, but essentially, we could now just go outside of this world, right? We think about the sequence data. Now, if we want to define one recurrent neural network in general, we can think of any neural network. So you don't need to think of fully connected or I don't know, CNN anymore. You could have any neural network. The only thing that you need is the memory component, right? So you need to get some sort of state variable, state feature out of this neural network somewhere in the neural network, and you feed it back every time to your input, right? So this is the only change you are making. Nothing is changing anymore. So you could have fully connected convolutional ResNet. You could have inception units that Google uses. Anything, right? That's okay. And the classical ones, I mean, the early ones which people started to use were fully connected. I mean, some people tried convolutional neural networks as well, but then transformers came out, and then we stopped using more complicated RNNs, and we just stuck to transformers. This is what you're going to see next chapter. So in the next chapter, you see that whatever we do here is a very good idea, but when the problem is simple, but when the problem gets advanced, then essentially we can just rely on attention. We basically don't need memory in this form anymore. But we're going to talk about this soon. So now we can have a shallow RNN, again, when we have one single hidden layer inside the base neural network. Or we could have a deep RNN. This is when you have a deep neural network and you start to do recurring inside that. And essentially, there is no serious change here. One typical change that we do is that we are using tanh as the activation usually in these neural networks. The reason is simply connected to the vanishing gradient. We're going to see that. Okay? So this is one thing. And the other thing is that we essentially need memory now. This means that we are doing a bit of modification in the input size, because now the input is not simply the input sequence, the entry of the input sequence, and the hidden state of the previous time, right? So you have two inputs going together inside the neural network. So you need to somehow do some sort of changes there. So let's start with one simple shallow neural network. So if we have a shallow neural network, this essentially means that I have the input. Then this guy goes to the hidden layer, and something comes out of the hidden layer. That is what is passed now to the output layer, right? It's a shallow neural network. It has only one hidden layer, right? And then that one is going to go inside the output layer to just compute the output for you. We don't care about that right now, because the only thing, I mean, we do know how to move in depth now, right? We already have played around with MLP and CNN a lot, so we do know that. The key point here is that we just want to do to make the recurrence here. And essentially, usually we replace the activation in this layer with tanh, as I told you. This is but not necessary. So you can do it also with other activations, but this is more popular simply because of gradient vanishing. And we do one basic modification. So here in the basic feed-forward neural network, the only input going to the hidden layer is your input x, but now you should somehow modify the input, not only taking x, but taking something like h as well, right? So x and h of the previous times are going inside the hidden layer, and the hidden layer is generating the next hidden state, right? So that is the whole idea. So we basically just need to modify in this form. So x goes at time t, hidden state of the previous time, and then the output comes output gonna evaluate the hidden state of the next time interval. This is one way of showing the diagram. So this is my favorite one, but some people also shorten it in this form, meaning that they say like there is one, recurrent connection from the hidden output to the hidden input. This is what I told you initially when we were thinking about the hidden layers. I told you nothing is going to get from one of the neurons forward backward to any other neuron, but now you can have it, right? So you can have loop inside the directed graph now, right? So in the feed-forward neural network, you don't have it. But yeah, this is just a notation, and you might ask me, is it basically the Elman network? Yes, this is somehow Elman network that we talked last time, one of the early networks. But there are two key points here. First of all, Elman used sigmoid function here, so he was specific about the activation. You can use any activation here. This is one thing. And the other thing was that the whole issue with Elman work was that he was not able, he was not able to train it over time, right? So you remember that he was using this approximation that he goes back, he goes down in depth, and then he doesn't go back in time, right? He stops there. Approximately, he says that the gradient of any previous hidden state with respect to any weight that I want to compute is 0 when I am at one particular time, which is easy in sense that you're going to reduce your computation, but then you are not learning the memory at all, right? So these are the issues with the Elman network which we want to resolve it, and we can actually go beyond what Elman did. So, okay, so you can think of deep recurrent neural networks. You can think of deep recurrent neural network, and this means that you can have more layers in depth, right? So for instance, you can start with, say, 2 layers. This is a simple connection. This means that the hidden layer or the hidden state of the first layer, hidden layer, is going to be dependent on its previous hidden state, right? And the second layer, the same, right? This is one way that you can do it. So I would like this diagram more because it's going to make it easier to understand. So when you want to evaluate or compute the first hidden output, you need to know what was the hidden output of the previous time interval, right? And the same thing for the second layer, but you don't necessarily need to do it this way as well, right? So you are now free to choose any sort of connection. So you can make skip connection in depth. So essentially, this is the idea of ResNet, right? So I don't need to just connect X directly to the forward going up. So I can connect X here, and then again, I skip this layer and add it up next, right? This is basically a ResNet. So every unit that you are using is a ResNet now, right? I can also make dense connections in time. So there is no need that my output or my hidden output at this time be only a function of the hidden output of that layer in the previous time. It could also take the hidden state of the other layers in the previous time, right? So for instance here, H1 also depends on the hidden state of the second layer in the previous time, right? You can do that. I mean, you're going to see that at some point. You ignore it, but you can do that in general, right? And you can also do skip connections over time, right? So meaning that you don't need really to always rely on only one previous hidden state, but you can also use 2 previous hidden states, multiple previous hidden states, right? So you can do it as well. All of these things you can do it, and you can replace these hidden layers with convolution or anything else. So that's only to just make you clear, when you talk about RNN, it is not anymore CNN or MLP that you think of a fully connected layer activation, fully connected layer activation, and so on, or a convolution activation, and so on. It could be anything, right? So RNN could be anything. It simply has a recurring in time. Everybody's clear? Great. Okay, so now let me start with a simple RNN for you, and then let's try to just somehow understand what is the challenge that we have when we want to get to learn the memory. And once we understand this, we are pretty much over, because you basically, once we see the challenge, then you're pretty much over, because there is no architectural new thing that you need to know. It's only about technical things. So I'm going to start with a fully connected hidden layer. And I think of a shallow RNN. Right now, you do understand what I'm talking about. It's essentially something like Elman network. And what I want to do, I want to just address what Elman did not address, right, at that point of time. So this is the thing. So this means that I have my input sequence. So it's a sequence in time t. And then the first input goes in, the first hidden state comes out, and then I'm going to have the first output. And my first hidden state is also initiated with some, randomly maybe generated, something that is freely chosen by me at the initial time, h0, right? And then this is going to be passed over time to the next time instant. And in the next time, I'm getting the next input. I'm getting the previous hidden state. I calculate the next hidden state, right? And whenever I need the output, I'm going to pass it up, right? But that is not that important anymore. So I am going to go on in time like this. So every time I am getting one input, previous hidden state, and then the next hidden state is going to be generated. I keep on doing that till I'm over with time, right? Okay? So this is essentially element network, as we talked before, when we think of a fully connected hidden layer. So the yellow box is here, fully connected. One thing that is important here for you, again, I indicated this last time as well. All of these networks are the same thing, right? So this doesn't mean that I have T different networks with different weights. They all carry same weights. Okay? So don't get confused. These are all the same thing. So this link here that you see is exactly the same link here, 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 and there, right? All of them are the same, right? Yes?
Aren't the weights changing over time?
The weights are not changing over time because the whole sequence is one sample that you have, right? Once you get your sample and you get your output, then you train, right? Correct? Yeah, when you have, say this is the whole sentence, right? If you want to train your neural network, you're going to give the whole sentence to it. You need to see the whole output, and then you compute the loss, then you update, right? So this means that when I am passing through time, here I have the same weight. I'm not changing the weight. I just go over the whole input. Now that everything is over, I do back propagation, compute the gradient. Now the weight gets updated. But once I update it, all of them update together, right? So the all outputs are going to change, right? Okay? Yeah.
Are the weights different for each entry?
Yes, over depth they are different, of course. But over time they are not different. So this guy is same as this guy, yeah? But this guy is different to this guy definitely. Yeah. And also this guy, the connection from previous time to this one, to this, like from H1 to H2, this connection is the memory connection. I'm going to break it down so you're going to see, but that is also different from this connection and this connection, right? But this one from, for instance, H1 to H2 is the same thing as the one from H2 minus 1 to H2, right? So the same kind of weight, exactly, the same component, right? At every time, I get one input from previous time. I multiply with one weight, one input from down, so the x. So I multiply with another weight, and then I just combine them, activate, and go up, right? So, but once I break it down, you're going to see. Yep.
As you have said, the yellow box is a fully connected neural network, right?
Sorry?
The yellow box. Right?
Yellow box, yes?
Is a fully connected neural network.
Right now, I assume he fully connected, right? But it could be anything.
So when you each time when the previous layer comes in, the weights there will change.
Sorry?
As the previous the result from the previous hidden layer comes in, it will like change the weights inside the fully connected layer or not?
No, it's not changing. I mean, the weight is fixed. The weight is fixed. All the weights are fixed, right? So as I said, like you give your sentence into your neural network, weights are fixed. So you do all of this computation, you see the whole output. Once you have your whole output, then you can compute the loss, right?
The output is the next word.
For instance, if you are thinking of sentence completion application, yes. This is exactly the same one. Or assume that you have a sentence and you want to just label every single word in it.
The Y is our target or just is simply?
It's the label. Assume that we have it. It's a kind of challenging way to define it. We're going to see it later. But right now, assume that you have it. Simple application, just assume you have a sentence. And the sentence, for every word, you have an a kind of label. Like we would say the first word is, I don't know, subject, the second word is verb, the third one is object, and so on. So if this is the case, then when I give you a sentence, I already have labeled it when you want to train it. So I give you one sentence, I am good, and then I say the first one, I don't know, is subject, the second one is verb, the third one is adjective, right? So I give you the label and the input, right? And then your neural network is simply doing classification. So every input comes and the previous one comes in. It's going to tell you whether it is subject, object, verb, I don't know, adjective, adverb, anything that you can say, right? And then you're going to classify it, right? Maybe initially it wrongly classify I as a verb, right? So it means that Y1 is classifying verb, right? And so on till the last one. And then you're going to see it, compare it to your true labels, which is subject, verb, adjective, and then you try to compute the loss. Now that you have the loss, you can train, right?
Okay, all the process here is just a forward pass.
Is a forward pass, exactly. This whole thing is a forward pass now. Yeah. Questions? Everybody's cool? Great. So now that you are cool about that, so this is basically what I was trying to insist now. So we have a bunch of weights, and these weights are repeating all over the time. So for instance, we have one set of weights which are connecting or hidden state in one particular time to the output, right? These are fixed. They do not change over time. They are fixed, the red weights, right? Then we have a bunch of green and yellow weights which are connecting. The green weight is connecting the current input to the current hidden state, and then the yellow weight is just connecting the previous hidden state to the current hidden state, right? So for instance, my hidden state is simply multiplication of each weight to the corresponding input activated, right? So these weights are not changing over time. This is only X and H which changes over time, right? Clear? Yeah. So I can basically learn this one and this one, right? And these are all the same all across the network, right? So it means that this is the same yellow guy as this one, and so on, right? It's not changing because each time, whatever I see from previous time, I'm going to multiply it with the same weight, add it up to the other linear transform, right? Now, one thing else is, are they the only things that I can learn in this neural network? The yellow weight, green weight, and red weight. Are they the only things I can learn? Any other thing that I can learn? Any guess?
Could you not make changes, like, you put in your sentence to something and you get something back? Couldn't you, I mean, I know this isn't like a learnable parameter, but maybe using a single fully connected layer isn't the best option.
Using a single fully connected layer is not necessarily the best option, of course, if your problem is complicated. But the point here, I mean, first of all, I'm thinking of a simple problem. But usually, the whole complication of these problems is not within the process of mapping, is in the process of capturing the time dependency. And you're going to see that later. Like, we have more sophisticated approaches to handle things over time, like gating. That is the best one you can do. But for now, you assume that the problem is simple, that I can do it. Yeah? Now, my question is, when I have this architecture, like what I showed you here, is there anything else that you think I can learn?
Biases.
Sorry?
Biases.
Biases, you can do it. They are included in the weights, right? But you can also learn the initial state, right? H0. Because H0, you just consider something, right? And you can leave it free as something learnable. Usually we don't do it, we just generate something random, but you can do it as well, right? Anything that is not supposed to be a part of your network generated variable, you can just learn, always, right? Everybody's clear? Yep.
So wait, what would H0 be? And like, if we're predicting the thing in a sentence, would H0 be the previous sentence, or like?
It's something. I mean, you can agree on something, like for example, in language models, we agree on like start of the sentence, right? So this is one thing. Start token. This is one thing that you can do, but you can also say that this is a vector, right? At the end of the day, each of these h parameters, h variable, is a kind of vector or tensor or matrix, whatever, right? And that vector contains a bunch of numbers in it, right? And then those numbers, you are not obligated to choose anything specific. So you can leave them as parameters, and then you try to optimize it. Yeah? Clear? Yeah, okay. Questions? Okay, great. So now that you have the feeling about the RNN, then the first thing that we want to do is we want to see how we can do the training on this RNN, right? Because now the problem is a bit different as before. We need to just pass the whole sequence. We need to wait for the output. And once we see the output, then we should be able to somehow propagate not only over depth, but also over time, right? So to do that, let's just consider some simple scenario. So assume that I am just generating x1 till as I have x1 to xt. So I am passing it over time through my network, and every time I'm getting one output from my network. So I'm going to get t different outputs from the network. And assume that I am giving you a sequence of length t of labels. Like for every single time instant, I have a label. Can I do it based on the cases I showed you? It's not necessarily the case, right? It's only possible when we have many-to-many problem type 1, right? But if we have many-to-many problem type 2, 3, or I don't know, one-to-many, many-to-one, this is not the case, right? So you have maybe less or more labels as the number of outputs you are getting, right? So you cannot say it for general, but the point here is that for now, just assume that. We're going to handle that issue later on, okay? Now, for the input, don't get confused. So I showed you this one-to-many case, and you might tell me that, okay, if I give you one input, then that's over. We don't have any input later, right? So there is no x2 to xt anymore. But this is okay. This is input. I can assume that all of those inputs are empty, right? I can agree on some specific input to just represent empty, like the vector of all zeros, for instance, in this example. And then I always put that empty input for the time that I don't have any input, but I still want an output, right? So input is not an issue. The main issue is usually the label. Yeah? This is the segmentation problem. We're going to talk about it later. So now that we have this, now assume that I have a loss function. And this loss function is able to get the whole sequence of the outputs and compute the loss between this sequence and the sequence of labels. Again, you might think of that easy example I told you last time, like you're going to compare every single y with the corresponding label and then compute the loss, then sum it up. If the problem is that easy, it's great, but it's not always the case, right? Because maybe you have a translation, right? It's a translation output, and the true translation is something else, but computing the loss between these two is a bit hard, right? So if I give you two sentences in English, they could be the same thing, but rephrased differently, right? So it's not that easy anymore to compute this loss. As I told you, this is hard. But for now, don't think about those complications. Assume that this loss is given to you, okay? We're going to deal with it later on. Everybody's clear? So now that you have this, now the key point is that I'm going to start from time 1, hidden state 0, time 1, and then I go all over time till I get all of my outputs. Now that I have all of my outputs, one sample is over. One sample has one long sequence, right? One sample is a complete sentence, for instance, right? Now, one sample is over, one sequence of outputs is there, right? And then you're going to get this sequence, you pass it through that loss function that you don't know yet what is that guy exactly. And also you inject all of the true labels you have. And this loss function has somehow the ability to compute for you the empirical risk, right? The loss, the value of the loss, R hat, right? So that's something that you do in the forward pass. Now you have your R hat. The next thing that you need to do is to compute the gradient, right? You want to know what is the gradient of R hat with respect to anything that you can learn in this neural network, right? So what are those gradients? Can you tell me? Weights, the green, yellow, and red weights, and H0, yeah? So essentially you have 4 different kinds of gradients. So you have the gradient of R hat with respect to the green weights, yellow weights, red weights, and you could also have the gradients with respect to blue state, right? You could have 4 different gradients, right?
Why does the gradient to the H0 be a specific another type of the gradient rather than the common yellow one?
No, they are basically the same thing. I simply mean that if you want to think of gradient, you need to compute the gradient with respect to all of them. Yeah? I don't mean that it's naturally or mathematically different from the others. It's the same thing, again, backpropagation. But I mean, at the end of the day, you want to compute these ones. So I want to again insist on this point that you're computing the gradient of this R hat with respect to this yellow one. And this yellow one is appearing all over the time, right? So it's not that you are computing the gradient with respect to multiple green guys, just there is one green guy, right? And you are computing the gradient with respect to that one. Yeah? So again, don't get confused with the time. This is very confusing at the first step, but if you just pay attention, you're going to get somehow feeling about that. Okay? Okay, so now what we need to do, we need to get from R hat back somehow to every single of these y's. And once we got to y's, then we can go backward towards those weights, right? So we have actually, I mean, you might tell me that this is a hard thing to compute this gradient of R hat with respect to all of these outputs because of the same, translation example I told you, how I can say what is the gradient of the loss with respect to one word in that translation, given that I could have different forms of translation. That is right, but we have a sort of solution for that. So for now, you assume that I can do this. So you assume that I can get backward from R hat to every single y. Okay? So you assume that that loss function is a very explicit analytic loss function, that I can write it down. And now I can compute the partial derivative of that guy with respect to any y that I have in this sequence, right? Everybody's clear? Yeah? So now that you have the gradient with respect to outputs, and the only thing that you need is to just go down, right? So now let's just consider the yellow guy, so the memory guy, which is our favorite one, this one. We want to get backward from these outputs toward this yellow guy. How can we do it? So I have R hat. I already computed the gradient with respect to I can compute the gradient with respect to all of these guys. Now, if I want to write down the gradient of R hat with respect to one of the weights, the memory weight, how should I open up the chain rule? Should I write it down for one value of y? No. R hat is now a function of y1, y2 till yt, right? So I should compute the partial gradient with respect to every single one, then multiply it with the partial gradient of that output with respect to the corresponding weight, and sum them up, right? Correct? So this means that I'm going to say, okay, R hat is a function of y1, so gradient with respect to y1 times gradient of y1 with respect to weight, right? Plus y2, y3, and so on till the last one, right? So this is chain rule, nothing complicated about that. And you assume, from my side, you take it that already we do know what are these gradients, the gradient of R hat with respect to y. Okay? Now, Now that I have this, now the problem again gets somehow like what we had last session. So essentially what we need, we can write it down in this form. So it's essentially the summation. And the only thing that I need to figure out is that how I can compute the gradient of every single output with respect to that particular weight, right? So if I can do that for all the outputs, then I am able to just replace it in this chain rule, and I get the gradient that I want, right? Okay, so that is now the problem, and I need to just go backward in time, and you already have seen it that this guy is actually depending. I mean, when we get from yt, we're going to end up with ht minus 1, and then from ht minus 1, ht minus 2, and so on, till backward. So here, I mean, this, I don't want to talk about it right now. You all know it, but I'm just indicating that it's just a somehow re-indication of the fact that all of these gradients that we talk here about could be of different mathematical form, right? They could be different objects, but you can always multiply them if you find the right multiplication. Okay, so we need to just do the chain rule starting from yt backwards so that we end up with some complete term in terms of chain rule for the gradient with respect to the particular weight. And this sounds like something very exhausting, right? So that's true. And because of that, I'm going to take help from my very good friend that, again, we're going to simplify everything. So we don't think about the very complicated problem, okay? So I'm going to make it a very simple like what we did in ResNet, because the only thing that I want to show you is the vanishing gradient property again over time, okay? So you see how I just mark it Albert Einstein here? So from now on, whenever you see Albert Einstein, you think of something super easy, right? Because always when I want to talk about easy thing, I show him up, right? This is the power of the market, right? Okay, so now let's just go on with the simple case. So in the simple case, I don't think of those weights and those states to be vectors or tensors or anything of that form. I assume they are simply numbers, right? Scalars. And this means that my y is simply this one, so the activated version of 1, 1 scalar. Again, my h is again scalar, given as the activated form of that linear combination. There is no bias, nothing like that, so everything's super simple now, right? Easy because now you don't need to really think about gradients and general product. You can think of derivatives, right? Now, if I want to do that, again, let's just draw everything. Now we have simply a scalar variable here, and then all of those h, y, and x's are scalar. And what we want to do, we want to find the partial derivative of one particular output at time t with respect to the weight wm, the weight of the memory, okay? Now, if we want to do that, how can we do it? Let's look at the terms. So yt is a function of, yt is a function of ht, and it's given in this form. If I want to get back to the weight wm, how should I write it down? What is the chain rule? So y with respect to wm, I can just write down y. What is the immediate variable that is carrying information? H. So I'm going to take the derivative with respect to h, right? And then derivative of h with respect to the weight that I want. Is there anything else? No. Yeah, W2 is a learnable parameter. It doesn't depend on Wm, right? So there is nothing else like that. So I'm going to write it down in this form. So yt to ht, ht to Wm, right? So everything fine. Now, this guy, yt to ht, you can easily compute it. So this is an immediate derivative, very easy to compute. So let's go for the next guy. So the next guy is ht with derivative of ht with respect to wm, right? And this is this guy, this term here. And you remember that we computed this guy once before, right? We did it once before. So you should pay attention to the immediate derivative and the nested derivative, right? So let's do it once again together on the board. just to make clear. So look at ht. So ht is a function of w1 xt wm ht minus 1. Which guys carry information about wm here? I mean, wm there is an immediate function. It carries information about itself, definitely, right? So I'm going to compute that immediate derivative, right? And then, in addition to that, there is one other guy which is depending on wm. And that is ht minus 1. So I'm going to write it down in this form. So I'm going to write it down. So my ht is a function, so is f of w1 xt plus wm ht minus 1. And I know that this guy is one thing, this is another thing, both of them carrying wm, right? So I'm going to write it down again, as I told you last time, maybe I of wm and ht minus 1, right? I write it down in this form, and then I would say, okay, the derivative of ht with respect to wm is the partial derivative of this guy, partial derivative of this term I with respect to wm, right? So when you compute the partial derivative, what do you think about ht minus 1? There's a constant, right? It doesn't depend at this point to wm, right? So you're going to write this down. So this is going to be multiplied with the partial derivative of wm with respect to itself, which is 1. So I don't need to write it anymore. So plus, the next term going to be ht minus 1, right? So it's going to be the partial derivative of I with respect to ht minus 1 times partial derivative of ht minus 1 with respect to wm, right? Everybody's clear? So it's not a complicated thing, but it could be confusing because wm is showing both as immediate variable and also inside ht minus 1, right? But this is the whole power of chain rule that is going to help you just go backward without the need to just nest in this ht minus 1 again as a function of wm and so on. So what I am doing in this slide, I mean, you can guess that I had lots of problems teaching this over time because people started to just get confused. And this is why I'm showing this whole ht exactly like what I did on the board. I'm saying that this is one function g which depends immediately on wm and the previous ht minus 1. And both of them depend on wm, right? And now you can use the chain rule. So the partial derivative of h with respect to wm is going to be the partial derivative of this function g with respect to wm times this guy. This is always 1. Yeah, you don't need it really. And then the partial derivative of that g with respect to ht minus 1, the other variable, times ht minus 1 with respect to wm, right? So now everything is clear, right? So we're not over yet with the backpropagation, right? Because we still have one guy, which is the partial derivative of ht minus 1 with respect to wm, which we don't know it. We don't have it yet, right? So that is going to be the case. So this is finally the term that you are going to end up with. And here I basically want to compute this whole thing for you in terms of, like, I want to replace this partial derivative of g with respect to wm and g with respect to ht minus 1. I guess you can easily do it, right? So that is like if I want to compute the partial derivative with respect to wm, what should I do? I'm going to get the partial derivative of the function f dot at the same point, right? Times the derivative of the argument, which is ht minus 1, right? Same thing for ht minus 1. Again, f dot times, this time is wm, right? So you can simply do that. So this first partial derivative is going to be ht minus 1 times f dot. Z is simply this long term, so I'm going to replace it by z. And now the other one is wm times f dot, is the same partial derivatives we have done before in the feed-forward neural network. So you're going to end up at the end of the day, when you replace everything here, you're going to get one derivative of your activation function at time t. You're going to have it. And there is there are two terms here. One of them is ht minus 1 itself. One of them is its derivative with respect to Wm, right? Clear? Questions? So everybody's clear about the chain rule here, right? Great. So if you're clear about that, so let's go for the next time. So I am okay here because I do have zt. Zt is basically computed at time t. This is what I have before activation. I have ht minus 1. I computed it when I was passing forward in time, but I yet don't have this guy, right? So I'm going to go backward in time. But if I go and compute this one, do you think that it is any different from ht, the derivative of ht? It's the same thing, right? ht to ht minus 1 is the same thing as ht minus 1 to ht minus 2, right? So I'm going to do that. So I'm going to go backward in time now. Again, I'm going to say, OK, I have ht minus 1 in this form, and I open up that partial derivative. You're going to end up with exactly the same term, same expression. So you're going to have your derivative of activation at time t minus 1 times ht minus 2 now times ht minus derivative of ht minus 2, right? And if you keep on going backward in time, you're always going to see this behavior, right? So the derivative of h at any particular time with respect to the memory weight is going to be this derivative of the activation at that time times previous hidden state plus the derivative of the previous hidden state, right? Everybody's clear? Questions? We can talk, right? We can discuss if you have a question. So everybody's clear about that, right? So we have done it a couple of times, but even if it is still not clear, just let me know. It's totally fine. Yeah.
I guess what I was wondering was, this is a simple example where everything is just a scalar. And
yes. Yeah.
I don't know. I guess maybe it's just the perspective of it.
Yes, but in the more complicated case, you just replace these guys with gradients. Well, yeah, a general gradient. Yeah. Yeah, it's going to be like a messy computation, but you rely on your computer, right? So that is not, I mean, I basically want you to see how it passes through time.
Okay.
Now, you don't need to complicate it in your mind. So it's going to simply get extended. But I see, you don't see it immediately. So this is why I just put this simple example here. Okay, no worries. Okay, so if we keep on going backward in time, we're going to get at some point of time to I equal by 1, right? And then when we write down this partial derivative of h1, it's going to be this term, h0 plus this derivative. And h0 now does not depend on Wm anymore, right? This is when you stop, correct? So you stop at time 1 because previous time is the initial state, and that one does not depend on Wm anymore, right? So you move backward all over time. This is exactly what we did also last session, right, on the element network. So now this means that at particular time t, then you come to your current hidden state, and you keep on going backward in time till you get all over the to the very input. But there is one key point here. And the key point here is that those derivatives that you want to compute in time, they are all given in a recursive form, right? Look at this expression here. So if I have the derivative of the previous time, then I can compute the derivative of this time, right? Or, better to say, because we usually move backward, when I move backward from very, very end, I essentially have the derivative of everything in time, right? Now, if I want to move backward, not from yt, but yt minus 1, I don't need to redo the calculations, right? Because I essentially have all of the previous gradients as well. Moral of the story, just go all over through time to the end. Start from the last time, move backward all over time, get to the beginning, right? And right now you have all the gradients that you need. So once you computed the gradient of last y with respect to the weight, then you essentially are able to compute the gradient of any other time, any other y, with respect to that weight. So let's look at it together to just understand it. So this is the very key point here, that everything here is in a recursive form. This means that when I want to compute the gradient of yt with respect to weight wm, what do I need to do? I need to know the gradient of ht with respect to that weight, right? But I do not stop there. I also need to know the gradient of ht minus 1 with respect to that weight, right? ht minus 2 with respect to that weight, and so on till I get to h1, right? Now, what if I want to compute now the gradient of yt minus 1 with respect to wm? If I want to compute the derivative of yt minus 1, I need to know the derivative of ht minus 1, ht minus 2, ht minus 3, till h1, right? So I already have them, because when I was computing derivative of yt, I had to compute them, right? Correct? So, moral of the story, you just move forward all over the time to the very end. You get all of your outputs. Now, from very last time, you just move backward to the beginning of time. You already have computed anything that you need, right? So it's not like I start from y last, go over time, and the y second last again go over time, right? Y second last is going to stop there, right? The deepest thing I need to do is the last one, right? Everybody's clear? Questions? So if you want to look at this diagram here, when I am at yt, I compute this one, and I go all the way back to here, right? Now, if I want to get from yt minus 1, once I come here, all of these red edges exist, right? So I don't need to recompute them, right? I just come one down, right? And everything is computed. Yeah?
I'm just curious. It's like something like dynamic programming.
Exactly. This is like dynamic programming.
We have a table.
Yes. Yes, yeah. But the point is that you really need to just get backward all over the time, right? Yeah. You cannot stop. Like you do the recursion, you're right, but you're gonna do it till you get to the beginning, right? Yeah, and then that's over, right? But you can somehow model it at that form, right? Yeah.
So the gradient of each, I guess, weight will be different, right, for different time steps.
What do you mean? Like h?
Yeah, HT. And
yes,
HT
of course, yeah.
And however, you said that the WM should be the same.
WM is the same thing, right?
Then when we trend that, will that different gradient impact to?
No, I mean all of those gradients are going to add up at the very end to one gradient. That is the gradient of r hat with respect to WM, right? You did all of these calculations to put it in the chain rule. And then finally, you get the gradient of r hat with respect to wm. And you update wm with that gradient. You don't care about the time anymore, right?
So don't do it like individually.
No. You compute all of it. You put it inside that backpropagation, the chain rule, and then you compute the gradient of your loss with respect to that particular weight. And now you update. Okay? No worries. Everybody's clear? Questions? So this is the idea of backpropagation through time. So you basically can do it by recursion. So you start going forward in time, and then once you finish with going forward in time, then you want to compute the gradient of every single yt with respect to a particular weight, right? And then you can always write it down in this form. So you're gonna just compute the gradient with respect to the immediate h, the hidden state at that time. Then you go in line 2, and in line 2 you just do recursion till you end up at the beginning of time, right? And once you're finished like that, then you're going to just stop at time I equal by 1. At that point of time, you have your gradient of that particular time. And then essentially, you just need to do it at the very, very last time, right? Once you do it, then the others I mean, for the others, you already know all of these terms, right? So you don't really need to go to do the recursion once again. Yeah.
When you say do the recursion, when you do the very last one, that's like the longest one.
The longest one, right?
And how do the algorithms store it? Do we store each step, the number?
I mean, you store it on the computation graph, right?
Okay, so when we actually do the recursion, it's not recalculating, it's using.
No, yes, yeah. I mean, you can do it by recalculating, but it's going to be extra calculation, right? Everybody's clear? Questions? No question? Great. Okay. Yeah, there is one point here, and the point here is that this guy somehow looks like the backpropagation over very deep neural network, right? But this deep neural network is not happening in depth, really. It's happening in time, right? So even a shallow recurrent neural network, if your input sequence is very long, is a very, very deep neural network in time, right? And you do know that any of them, any deep neural network, could show vanishing or exploding gradient, right? It can show this behavior, and this is also the case here. You again could have vanishing or exploding gradient here. This is exactly what this was actually first observed. I mean, the exploding and vanishing gradient was first observed in recurrent neural networks. And then people got the time to make feed-forward networks very deep, and they actually projected this idea there as well. So that is the idea of vanishing gradient over time. So maybe we could have a couple of minutes break, and then we just continue. So, shall we go on? So, now, if we go over time, deep over time, then we essentially could have vanishing gradient. And it's not that different. I mean, mathematically, it's the same thing. But it's going to show different impact when you have vanishing gradient over time as compared to the one you had in depth in sense of the kind of behavior you're going to see in that neural network. So what is that? So if I go backward in time, I mean, we started with this guy. We routed down in terms of the previous hidden state. And we kept on going like this over time, right? So if you want to just get this final expression, it's going to include all of these terms. So the gradient of yt with respect to wm going to be all of those partial derivatives we computed, multiplied next to each other and added up. So you're going to end up with such terms, right? So you're going to have, so this is the immediate one. Then you're going to add it up with the gradient of the previous time, right? And then this is going to show up the accumulated version of time t and t minus 1. And wm is going to show up there. And then, again, you're going to go for the next previous time. So you're going to have 3 time components now. And so on until you get up to one particular time, say I, right? So I times before, then you're going to have such accumulation here, right? And now, if I leave this neural network to go very deep in time, then at some point of time, you expect that these terms, I mean, they are multiplication of lots of different activation products, right? And these terms are going to get very small. Again, if we assume that the activation function is something whose derivative is smaller than 1, like sigmoid or tan h, right? So if you do that, then you're going to see that this expression here that you have, you see, this is the summation of lots of terms. And as you go deeper down, every single time, every single expression is getting more and more accumulated version of this product, right? Now, if I let the time goes backwards forever, then some of these terms are going to vanish, right? And some of them going to remain, right? So if time is very deep, the first term is not going to change because it is not deep in time, right? It's just carrying one derivative. The one which is going to vanish is when I am far away from time t, right? Everybody's clear? So if I look at this term, this is what I have as a kind of term inside my whole argument. So I have some of these guys over I, right? And then if you think of this term, then this term again, if f dot is is larger than 1, so you're going to accumulate more and more and more, so it's going to explode. But this is not, again, the particular case we're interested in. The other case is when you have it is smaller than 1. And when you have it is smaller than 1, like what we did in resonance chapter, it's going to get smaller and smaller over time, right? Meaning that it's going to get, it's going to vanish at some point in time, right? But key point here is that you should always pay attention to this expression here. So when this guy is vanishing, anything after that in time is vanishing, right? So if I get backward in time, somehow say at 10 intervals before, I start to see the vanishing. So the gradient is very small. Anything before vanishes, right? Any other term, so any other term here in this summation afterwards, they are all going to be pretty much 0, right? But you still have these terms from 10 intervals before to your interval, which are not vanishing, right? So they are being there, right? The first, second, third term, they are there because they do not have too many derivatives, right? The terms who are going to vanish are the ones which are far away in time from you, right? Clear? So this was also pretty much the case in depth, right? So the derivative of the immediate previous layer is not going to vanish, right? The last layers are not vanishing. The initial layers are vanishing, right? Here is the same thing, right? But in time. Everybody's clear? Okay, so if you see that, then you might ask me, is there any solution to this one? Okay, and the answer is yes and no. Okay, so what do I mean by yes and no? On one side, you cannot actually, in this particular network, you pretty much cannot do anything to resolve this issue effectively. Yeah? At the end of the day, you're going to get the vanishing in time. Okay? But the point is that you can always come up with new ideas, new sort of structures, architectures, such that it's going to vanish somehow very late so that you are carrying enough information. Okay? But the key point that I want to indicate here is this particular argument here. So one thing that you should see in vanishing gradient over time is that it doesn't mean that you are not getting any gradient. So you are at the end of the day getting some gradient, non-zero, right? For any weight that you have. Because the first terms in time do not vanish, right? It's only deep terms in time that vanish. But what does happen when this is the case? When all of those old terms vanish, what do you think that is happening now?
It has no memory.
Great. Yeah. As your friend said, you are losing memory, right? So your gradient at this time is not really depending on very past of your sequence, right? So vanishing gradient is again here, but it doesn't mean that the weights are not getting updated. Because this was the case in depth, right? So when you see vanishing gradient, early layers are not getting updated, right? But here, since you are not going very deep in depth, all of the weights are there. I mean, they have gradient and they get updated. But they do not get updated with a very past memory. They just get updated with a part of memory, right? The recent memory, the most recent one. Yeah. Yes, but not always is the case. Like if you remember that example I gave you, Yulia, and then at the end you wanted to write her. If Yulia has happened a long time ago, you want to keep it, right? But your argument is correct. This is why I say yes and no. At some point in time, probably there are things that you don't need it, right? And any intelligent creature has a kind of finite memory, right? So any intelligent creature starts to forget things happened very long time ago. But we as intelligent creature might remember things happened at 3 years old, 3-year-old to us as well, right? Because that was important, right? The first thing happened in my childhood, I might remember it, but I don't remember every day of my childhood, right? This is the point. So you want to have peaky memory towards back, but this is true that you don't gonna carry all the information of past. And here the whole issue is that the architecture we are proposing is somehow treating all things in the past the same. And this is how, gating is the way that we resolve it. Yeah.
So it's safe to say it's inherently challenging to learn H0 because it's so far away.
H0 is quite challenging to, at the end you're gonna have Y1, right? And Y1 is not far away from H0. Again, you can do it, but H0 is going again to be learned with the next few labels, right? Not all the way to the end. And it's again the same thing, so it's not going to impact for the whole rest of time equally, right? So everybody's clear about this vanishing over time? So vanishing over time, this simply means that your memory is now limited, right? You can't just carry information from limited past, not forever, right? And this is something not always a good thing to happen. So what are the approaches which we can somehow deal with vanishing gradient through time? So there are a couple of approaches. People try it a lot. And this is one of the kind of, funny and at the same time very educating story in the history of machine learning, that people started to see this quite later on when they started to believe on machine learning somehow and trying things, right? And they started to see this, but then they got into different approaches. Like, for instance, they started to use tanh because they see that this tanh has a kind of property that those extra terms that are getting added up, they are going to vanish later. So there are, if you check like old textbooks on machine learning or statistical learning, you're going to see that this if you draw the drop of the weights over time, you're going to see that this is going to be one of the slowest ones is tanh. And people started to say, okay, maybe we use tanh, so we're going to keep a bit of more memory. This is one of the idea. One other idea was truncated backpropagation through time, so you don't go all the way to the end and then move backward and update. You just go a bit over time. You don't go to the end, right? And you stop there, you move backward, you update. Okay? Again, you start a bit forward, you go on, you move backward a bit, you update, and so on. So you're somehow carrying information slowly over time, right? So you're shifting information over time. This is what we call the truncated backpropagation through time. Well, at some point of time, it was a thing, right? Now it is not. Okay? But the most sophisticated approach came out was the gating approach, which is somehow interesting because this guy was a master thesis of one very famous nowadays guy who is nowadays a professor in Technical University of Munich. And at that point of time, nobody was thinking about this. So he came out with the idea of gating. He proposed one computational model. He tried to train it given the very small resources that he had at that point of time. His supervisor, Schmidhuber, if you search his name, he's one of the very well-known figures in computational machine learning. And he just started to see that people are doing, very much nonsense efforts to just resolve this issue. And he somehow got reminded of his students' work. So he said, like, okay, look at this very old work of my master student. Like, it's a master student, you don't care, right? So look at that. And then it came up, the LSTM idea. So LSTM idea was proposed way before this, right? Way before any of even ResNet, these things that we know nowadays now. And he was somehow implementing this skip connection through time without knowing it, but with a kind of intuitive approach. And nowadays it's a thing. So he did it, I think, in 80s. It got somehow famous end of 90s. So he had to wait around 20 years to get famous. But the point was that many people are now exploring new venues to resolve issue, even though it's already there in the literature. And this is one of funny stories, but educating for many people doing research, because you don't always need to come up with innovative things, right? Sometimes you interpret the problem properly, and maybe you look backward in the literature, some other community, you're going to find out a solution which is already established there. So let's look at this idea of gating, which is a very intuitive and interesting idea. So let's get stuck to the architecture that we had. So we had this architecture over time, everything is scalar, easy. We can simply deal with that. So now, again, when you use this architecture, you pass through time. You have everything here, all of the hidden states, all of the outputs here. And this HT is essentially the memory that you are carrying over time, right? And we have seen that this vanishing gradient impact is going to somehow stop us from updating our weights with very long memory, right? This is the issue. So how can we resolve that issue? So let me just give you one intuitive, interesting example. This is our initial example. I guess this example is going to make everything clear for you about gating. So this was the example we had. Julia has been nominated to receive Alexander von Humboldt Prize for, we want to write her here, right? This is one we want to predict, correct? Now, one question. When we update our memory, say we have this, picky memory as intelligent creature. So we got to Julia, and then we see this is the object of this sentence, the thing that we are talking about, right? Now, we keep this in our memory and say that somehow a genie told us at some point in future, you need to talk about the pronoun regarding the object of this sentence. So we do know that we should keep Julia in mind, right? So from Julia on till I get to the point where I want to predict her, I essentially don't need to update my memory, right? Because none of these words here has been nominated to receive. These are not related to the task I want to do, right? So if I was able to just pick that point in time, I just stick to Julia up to that particular point that I'm updating, then I would be happy, right? So this is the whole point. So I should not do update if I'm just looking in this particular task, not a general task. In this very particular task, I obviously don't need to update anywhere here because none of these guys is going to help me predicting her, right? Clear? Now, can I do this? Let's just try one thought experiment, okay? Just let's assume that we have a genie who is going to help us. How we can do it? So let me, in addition to this whole thing that we had, the x's, the hidden state h, the output y, let me also define one other sequence. And that sequence is something that I call it u, okay? This is the axis sequence. I call it axis sequence, just a made-up name, okay? Axis sequence, this axis sequence has entries which could be between 0 and 1, okay? It could be 0, anything, any number between 0 and 1. Any idea how I can make a number between 0 and 1? How can we do it? You as machine learning experts? Sigmoid, right? So you're going to use sigmoid, right? Output of a sigmoid. But now, UT is something between 0 and 1. And what I'm going to do, I'm going to use the genie. So I get into term Julia, the word Julia, at time t0. And I set this axis variable in the sequence to be 1. So u at time t0 is 1. Okay? I do it. You don't ask how you do it. I'm going to explain it later. Now, I tell you that I can do it. Okay? Now, once I do it, so I put ut0 to be 1. Now, from then on, whenever I get to the next time, I just set my axis variable to be 0. Okay? So from next word after Julia, I keep axis variable 0. So the next axis variable is 0. The next one in the sequence is 0. And so on till time t. And t plus 1 is the time when I want to predict her. Right? Clear? Now, then, instead of using the this is the classical L-man-like architecture we had, right? So we just start with initial state. Each time we compute a new state, which is a superposition of our input and our previous state. We add them up, activate them, and then immediately we compute the output from this guy, right? This was what we did in the L-man-like network, right? Now I'm going to call it h tilde, so I do not immediately give it to the output, but I'm going to average it using u. What does that mean? I'm going to multiply that axis variable is something between 0 and 1, right? I'm going to multiply it to this value that I computed right now, my hidden state. And also, I'm going to multiply 1 minus u to the previous hidden state that I had. Everybody's clear? Everybody's clear what I'm doing? So you see line 3, right? Line 3, what I'm doing, so h tilde t is what we used to compute up to now in the L-man-like network, right? That is the one, the hidden state. No, I am not simply getting hidden state and compute the output out of it. I'm going to get this new hidden state I computed. I average it with the previous hidden state, ht minus 1, and then I give it to the output. Okay? And how I average it, I use my axis variable. So if axis variable is close to 1, essentially when u is exactly 1, this term is going to disappear, and this is basically the same thing as L-man network. But if I set u to be something smaller than 1, then I am carrying a bit of information from previous time, right? Everybody's clear? Okay. Now that you got the idea, let me just see what's going to happen when I use my geniated axis sequence. Okay? At time t0, we said axis sequence is 1, right? This is the moment Julia happened in the sentence, right? So I'm going to get to Julia, and then I compute this h tilde t0. This guy is going to be a function of x t0. X t0 is the input which is proportional to Julia, right? So this means that this h tilde variable, this hidden state of time t0 that I compute, it has fresh memory of Julia, right? Julia just happened, right? It's in x. It has a fresh memory of Julia, right? So this h tilde going to have a fresh memory of Julia, and now I want to compute my true hidden state h, not h tilde, but h. How do I compute it? My axis value is 1, right? So 1 times this blue hidden state plus 1 minus 1 is 0 times the previous hidden state, right? Everybody's clear what I did? So what's going to happen? My hidden state is exactly what I computed now, right? And this hidden state has fresh memory about Julia because in its input x at time t0, the word Julia happened, right? Everybody's clear? Questions? Yeah?
The previous t0 minus 1, that hidden there is not defined, right? So
Sorry?
that the h t0 minus 1
Yes.
instead is not defined.
It's defined. It's ht, not h tilde, h, right? This is the hidden state you have. I mean, this ht0 is going to be the previous for the next one, right?
But we start from the Julia, right?
No, we did not start. We started from the beginning of the sentence. We just came up till we got to Julia, right? And then from Julia on is like that, okay? Yep.
We're not saying that we only have to pay attention to one thing.
No, we do not assume that. Right now I'm telling you that a genie told me. Then you're going to make this genie happening, right? But right now I assume that a genie told me, okay, Julia is important, keep it.
Yeah. But potentially we could have every word need to be paying attention.
Yes, we could have. We're gonna see it later how you can pick good words,
But
right?
I think it means that we need to set up a gate for all of these words.
Yes, essentially you're gonna do that. So you're gonna give a gate,
Yeah.
and then you're gonna learn. You're gonna leave the gate to get learned with data. So then you give a lot of sentences to your to your model, and then it's essentially start to understand where it should pick, where it should not pick.
So does the number of the gates increase when we are?
Not necessarily. I mean, you can increase it essentially. But LSTM works with only 3 gates, and it's already considered to be very complicated. So you don't need to really increase it too much. But as long as you have a gate, it's going to help you pick some parts in the memory. Yeah, no worries. But more sophisticated approach is the attention, the idea of attention, which shows up in transformers. We're going to talk about that later. Okay. So everybody's clear now? So our hidden state, ht0, has a fresh memory about Julia, right? Now, let's go for the next time. If I go for t0 plus 1, the next time, the next word in the sentence. Now, I am going to compute h tilde t0 plus 1 exactly as before, right? So I'm going to give that ht0 and xt0 plus 1 to my hidden layer. I compute h tilde t01, right? Once I computed it, now I want to compute not h tilde, not the blue guy, but the black guy here, ht0 plus 1, right? I want to compute that term. And this term is going to be the axis term times the blue term plus 1 minus axis times the previous hidden state, right? Correct? Everybody's clear? And now, I told you that I put the axis variable to be 0. Since it is 0, then the next hidden state is going to be 0 times what I already calculated in this time, plus 1, what I already calculated at previous time. And that guy had a fresh memory of Julia, right? So This next guy has, again, a fresh memory of Julia. I didn't touch the memory of that, right? If I keep on going till I get to time t, what's going to happen? You always have the same thing, right? So as you keep on going every single time, you're just averaging with this access variable 0. This means that t01, the hidden state, going to go for time t0 plus 1, t0 plus 2, so on till t, right? So when you are at time t, you have again fresh memory of Julia, right? And now you want to update. So at time t, you're going to compute this one. And you want to just, sorry, so you want to now predict the next word at t plus 1. And when you want to do it, you already have the fresh memory of Julia. So is it more probable, more likely that you predict the right word or in the element network? In this network, right? So this idea that you can have one access sequence, and this access sequence is somehow controlling how much of information at this time computed is going to be carried out over time. This is the idea of gating. And why we call it gating? Because we think that we have a tap, right? A gate. And then you can play with it. Just the whole thing goes out, or I just close it completely, nothing goes out, right? Clear? So that U is actually the gate for us here. So UT is the thing that is gating the memory, and at every single time is going to tell us this H tilde is the information I computed at the particular time. HT minus 1 is the hidden state of the previous time, and I'm always gating between them. Like I have the choice that I ignore whatever I had right now and pass everything on. I have the choice that I ignore whatever I had before and pass what I computed right now next time, or I have the choice to just make a balance between them, right? And this is essentially going to help you a lot getting rid of the vanishing gradient. You might say, why this is happening? Because this is implicitly implementing skip connections over time. How is it the case? This was our recursive expression when we were backpropagating over time, right? The gradient of hidden state at this time was given as in terms of the gradient of the hidden state at the previous time, right? Correct? But now, in my example, since you have all of those u values, 0, from t to t0, what's going to happen when you want to compute ht when you get from t to t0 backward? Every time you are just averaging with access variable 0, right? This means that your ht plus 1 is same as ht, right? ht is same as ht minus 1, correct? So just look at it here. Here it was my ht0 was this guy, right? And then next time it was again the same guy, right? And I kept it all the way till very end, right? So when I got to ht, it was again that one, no? Right? So now when I'm computing the derivative of ht with respect to anything, that ht is essentially same as ht0, right? ht0 is the same thing, right? So it's derivative of ht0 with respect to that thing. So it means that I am just skipping a couple of time, just jump somewhere in time backward, right? Everybody's clear? So as long as you have your gate equal to 0, then for any of them, you just immediately move backward. And there is no extra term getting multiplied. This is going to help you avoid vanishing in time. Everybody's clear? Questions? No question? Yeah.
So this gate index, it fulfills your wish that for that sentence with starting with Julia, it's just remember the Julia and skip all the words in between, right?
Yes. Yeah. Somehow the gate is telling you right now that when you want to predict her, you don't need to know all of those words. You just need to know Julia, right?
So all the words in between is ignored, right?
Yes, they are ignored. And you might tell me, okay, maybe in future I need to do something with those words. You are totally right. We're going to I mean, this is just a dummy example, just to give you the idea what is happening in gating, right?
So in practice, so we are not, this gating is just a supplement for the vanilla RNN, right?
Yes, exactly. It's going to somehow modify the architecture of the vanilla RNN. Exactly. Yeah, exactly. So, everybody's clear? Questions? No question? Okay, great. So if you got no question, I mean, that was a very interesting idea, but my question is, how can I find this UT? How can I find the gate? And you tell me, as people expert on deep learning now. I want to make U. I know that U is going to help me, but I don't know how to do it. How do we do things that we don't know when we...
Validation.
Sorry?
Validation.
I mean, validation is later on, but initially when I want to just make it a function like U there, what should I do? Learn that, exactly. So this is what Vapnik says, right? You know Vapnik? Vapnik is like this famous guy who proposed SVM, VC theory. He says, he has a very famous sentence, let the data talks itself. Okay? So this is the thing that we're going to do. We're going to just learn it. Whenever you don't know something, how can I make a U? Okay, just propose one architecture which gives you something at the output like U between 0 and 1. And once you do it, then you leave it learn, right? You just put some bunch of weights there. You leave it get trained over data, right? And somehow that architecture, hopefully, is going to understand how it should do the gating, right? So the genie for us is always something learnable, right? And this is the same thing here. And as you said initially, you can always do it using a sigmoid function, right? The output of a sigmoid function is always between 0 and 1, right? And now, if I want to just make a gate, I can simply put some argument in between. I don't care what it is right now. I just compute the sigmoid function of it. I activate it by sigmoid, and that is going to be my gate, right? So this is a kind of general form of a gate. So a gate is going to get your input at time t, your previous hidden state. It's going to multiply them with a bunch of weights, right? Those weights are learnable. You can potentially add some bias here as well, or you can ignore it, right? But all of these parameters are the things that you can learn. And how you can learn? You just do backpropagation, you compute the gradient, and you update, right? You start with some random thing, and you let it update. And now, the output of this guy, this gamma, is going to be something between 0 and 1, right? And that thing between 0 and 1 is going to be your gate, right? Now, what should be the dimension here? It depends what you want to gate, right? If you want to gate a vector, then you need to compute a vector here of the same dimension. Then you just apply sigmoid on every entry. You're going to get a vector between 0 and 1, every argument, every entry, right? And then you just do the entry-wise product with that next thing, right? If you want to gate a tensor, then you compute a tensor inside of the same dimension. You just activate everything by sigmoid. Now you have the same tensor, everything between 0 and 1, do entry-wise product with whatever you want to gate, and then you're going to get the gated output, right? So the dimension of gamma here is no more of discussion here, right? It totally depends on what you're dealing with. In the dummy example we had, that gamma was just a simple scalar, right? But in general, you can think of any mathematical object, right? And all of those mathematical objects can be made by a bunch of weights, given the input that you have and previous state that you have. And then you can essentially just build this gate object and use it to gate your information. Everybody's clear what gate is doing? Questions? Yes?
The notation of gamma t is basically equivalent to U of t.
U, yes. Gamma is now U here. Yeah, maybe it was a better idea if I use gamma as well there. So
The weight here is different from
the other weights that you have. It's a separate weight that you learn it, and it's going to help you understand when you should gate, when you shouldn't.
then how we know gamma is the function of xt and ht minus 1.
Because at every single time, the things that you have are the input at that time and the whole memory you carried from the previous time, and that is your state, right? So these are the things that you have. I mean, in LSTM, we're going to add one extra thing, but essentially whatever you have as the information at that time, you can just feed it in. If you have more information, you can also include them. And they're going to have their own weights. Yeah? Yep.
So what is the general learning procedure for this gamma t? So it is added to the previous loss function or something?
We're going to decipher it. So we're going to have GRU and LSTM, and you're going to see how each of those architecture use gates. So there is no single gate there. I mean, there are multiple gates in one architecture. Okay? But this is obviously the topic of next session. Okay? So, any questions? So, moral of the story, this is the gate. You can always make it. You can learn it from your data. Anything in this gate is between 0 and 1. This is what we want. And this is going to be of the same dimension as the memory variable that you want to gate, right? Anything that you want to gate, you just can make one gate variable for that one using a sigmoid function and a bunch of weights. So there are famous architectures which we call them gated architectures. What does that mean? That means that they are having some gates inside them. The most famous ones are GRU and LSTM. You can come up with your own architecture if you need. It's just a gate, right? You just feel like I need a gate here. You're going to put that gate there, right? And you leave it to get trained, and hopefully you can learn what you want to do, right? So there are two things, GRU and LSTM, which are the most famous ones, and they are still being used for simple sequence-to-sequence applications. So we are going to talk about these two guys next time, okay? So this is going to be the topic of the next time. So for the next session, I'm going to talk about these gated versions, and then we're going to talk about the bidirectional RNN, so how we can do it bidirectional. This is very quick. And then we are over with that. But I told you always, yeah, you have output, you have labels, you want to compute the loss, but you don't know how to do it always, right? This is the problem of segmentation. Segmentation problem, I'm going to explain what the problem is. But the solution is rather complicated. So I'm going to leave that for you, yeah? Because this is not something very practical nowadays, the CTC algorithm. But it was one of the very important breakthroughs. So I'm going to explain you next session what is the segmentation problem. And I'm going to give you a rough idea how they got to solve it. But then I'm not going to open up all the maximum likelihood detection, things like this that are inside it, because these are not going to just add too much to the knowledge you need. Okay? So I'm going to skip it before. I mean, we're going to have that up to break. And after break, I'm going to start with seg-to-seg models because I want to spend more time on transformers, and they are more of practice nowadays. So you're going to probably benefit more from that. Okay? Everybody's clear? But from my side, CTC, I'm going to indicate it once again. Next, CTC is one of the greatest achievements, I mean, theoretically, in this computational machine learning. So it's always worth just taking a look into it and see how this very complicated problem finally got solved with a bunch of, really smart people. So that's it for today. See you on next Tuesday.